you are seeing there are shear connectors and composite steel deck and concrete slab placed over the steel girder. Another figure or another photograph shown here, the filler beams, steel decks, concrete slabs. Here again from another view. So we can have reinforcement also. Here it has been shown. In the metal decking, we can have the reinforcement. Of course, in this metal decking also, we can have certain arrangements so that there's a bit of more shear connection. We'll see that more of bonding. So at these shear connectors, they're mostly called shear stud, and they have a head here. And the purpose of this head is that it doesn't allow the concrete to move away from the steel. So it's a sort of locking arrangement. We'll be discussing that in detail later on. This is a real photograph taken by myself at some point of time. And here you can see a lot of shear connectors here. And you are also able to see here a composite metal decking. And of course, the concrete is about to be placed over this profile sheet. Of course, below the profile sheet are the steel girders. And these shear connectors, they are all along the steel girders. So the steel girders are like this, because these shear connectors have been already welded to steel girders. And once the concrete will be cast here, there will be a composite action. We already discussed the advantages, so we're not going to that. One of the major disadvantages of composite construction is the shear connector installation. They're not conventional material. The material of this shear connection is not conventional steel. It's a high strength steel, and the conventional steel has a strength of about 250 Newton per mm square. The strength of these shear connectors is mostly more than 500 Newton per mm square, and mostly they're patented items. The conventional welding methods also don't work here. So we need to have separate arrangement for the welding methods. Now this is a close-up of a composite metal decking. And you are seeing here there are certain deformed ribs. And these ribs also have their own purpose. They ensure a bond between this metal deck and concrete slab. So at certain point of time, these metal decks with ribs are preferred. But in some construction sites, metal decks without ribs are also considered. They are just giving a bond which is over and above our analysis part. And they are also again available in standard shapes and size. And Eurocode defines their properties. Here you are seeing the metal decking which doesn't have the deformed ribs. But again, this is also in practice for the construction purpose. Only thing is, the bond here between the steel, this profiled metal deck and the concrete slab will not be that much good, which will be there with the deformed ribs. So they are also called sometimes non-composite metal decking. Composite here doesn't mean the composite action between the structural steel and the concrete slab. Here, for this definition, the non-composite metal decking, or this nomenclature, here the composite is meaning the composite action between the profiled sheet and the concrete slab only. It is nowhere defining the complete composite action of the section. Now, this installation of metal decking is also quite important, and they have to be placed at predetermined point in erection sequence. This is a photograph of a shear connector, and they're also commonly referred to as studs. They're available in range of size, material, and grade. Of course, it is not that their size and their grade or their geometry is random. The standard codal provisions and which define what should be H by D ratio, that what should be the ratio between height and diameter, and then what should be the maximum diameter, what should be the maximum height, what should be the spacing between the shear connector, both the transverse shear connector and both the transverse shear connectors and the other, both the transverse spacing and the longitudinal spacing of the shear connector. Okay. And most popular type of shear connectors which are available in the market are called as Nelson shear studs. Typically, their standard size is like 18 mm dia and 90 mm to 100 mm height. So again, you are seeing here, they create a strong bond between steel beam and concrete floor slab. So here you can see a lot of shear connectors. They are placed very near to each other. Again, the placement of concrete here is also an art. You have to put the concrete in a particular manner. The reason is simple because until the concrete attains its strength, the structure is not a composite structure. It is just a steel girder. So if you apply a load on the bare steel girder, there will be permanent deformations due to that. So you have to apply the load in a particular fashion so that initial deformations in the bare steel girders are minimum. And of course, there are certain guidelines that the construction joint should be located over the beam or girder webs. And mid-span shoring should be placed. Shoring, there are two types of composite construction again. One is shored construction, another is unshored construction. Of course, if you are going for unshored construction, then the deflection will comprise of two parts: deflection due to bare steel section and the deflection due to the composite section. Whereas if you are going for the shored construction, the final deflection will be the deflection due to the composite action only. Now there are certain quality checks also which are specified in different codes, and like you can weld two sample studs, you can perform bending test. Again, we'll be considering that in the next presentation. Again, the scheduling of composite construction is also very important, because the point is, until unless the parts or the structural members become the composite members, it depends a lot. The deflection depends a lot on the manner in which you are going to apply the load on bare steel sections. So that's also quite important, and we need to look into that also meticulously. Another interesting part of this composite construction is the cambering. So it is more or less related to pre-stressing in the concrete. So what is done in cambering is that, after the load, there's going to be certain deflection, and the steel girders are going to bend in a certain direction. So as we do in the pre-stressing, the same can be done in this cambering. We can provide a deflection, or we can provide a curvature in the opposite direction, opposite to that direction in which we are going to expect the final deflections. So this is what is done in cambering. Again, this cambering can be done for a certain percentage of dead load deflection, full dead load deflection, or full dead load deflection plus certain percentage of live load deflection. The phenomena is same, or the philosophy is same as for the pre-stressing, but there are certain disadvantages of this cambering also, because it's not that simple as it looks in the photographs or as it looks on the slides. There's a certain complexity which is involved in detailing, fabrication, and fit up associated with moment connections. And mostly we should not use the cambers in the moment connected beams. Now, beams with simple framing connections, of course, they may be cambered because the end rotational resistance there is quite small as compared to that of moment connection. Again, the next question is when to camber. So we can camber girder beams, we can camber members with uniform cross sections, we can camber the filler beams, or we can camber the composite floor beams. And when should not we camber? That is, one is cantilevered beam should not be cambered, and the moment connected beam should not be cambered. Similarly, braced beams also should not be cambered. So as we are very particular in pre-stressing of concrete beams, that we go for pre-stressing in certain situations only, the same needs to be done for the composite construction. Now, this cambering can be done by two manners. One way is to go for heat cambering, where we apply heat to small wedge-shaped areas at specific increments along the beam. And the beam is placed upside down on the support so that the bottom flange can be heated. And the heat flange, of course, will expand under the heat, and it will contract as it will cool. And this will induce a camber in the opposite side of the beam as this will cool. So heat cambered beams can be used in the manner in which it is shown here. So you are seeing that part which was heated, that is on the downside. Of course, during the camber, it was on the upper side because it was put in upside down manner. But finally, it's going to be on the lower side, and that is a concave down orientation. Along with the heat cambering, there's another option of cold cambering. They are more widely used and they're generally economical than heat cambering. So here, of course, you have to mount the beams on the frame and then you apply force from rams to bend the beam to create the cambers. Then there's a natural mill camber also, because when you'll be transporting the steel girders from the factory to the construction site, there will be a slight camber in the beam because it's taking the load of the beams which are there lying on it. So you can take into account or you can take the advantage of that natural mill camber, but that should be at least 75% of the specified camber. Otherwise, you have to go for further cambering. And this is a typical manner in which cambered beams are shown in structural plans. Like here, it has been shown like there is a 3 by 4 inch camber at the center of this beam going in X direction, and then there's a camber of 1 by 4 inch in the center for the beam which is going in the Y direction, 1 by 4 inch. So these are the standard practices to show the camber on a steel girder, so which are going to be composite finally. And of course, the quality control is to be ensured as per AISC, American Institute of Steel Construction. It may be noted that in Indian standards are still way behind the AISC Code of Standard Practice or Euro codes. Of course, recently certain codes have been introduced for the composite construction. But yes, that sort of detailing is still missing in Indian standards. Then we have to see the cost of cambering also, and that has to be compared with the additional concrete due to ponding. What is this additional concrete due to ponding? Actually, it will not do the initial cambering. Then when we'll be placing the concrete on the bare steel section, the steel will bend and that will cause a curvature in the concrete slab. That means the effective depth of the concrete, which has to be filled on the concrete slab, will increase a little bit by the amount of deflection into that area. So that is called ponding, additional concrete due to ponding. So you have to see the additional concrete due to ponding vis-a-vis the cost of using shored construction, vis-a-vis the cost of using a heavier section that does not need to be cambered. And then you have to calibrate and see which is beneficial for you. At times, it may happen that you can afford the ponding. At times, it may happen you can afford a shored construction. At times, it may happen that the cambering is a cheaper option. Now, just to get rid of all these problems which arise due to the casting of concrete on site, that is in situ casting of concrete, people have moved away ahead and they have gone for the prefabricated concrete slab. So what's done in prefabricated concrete slab is we do have prefabricated concrete slabs of standard shapes and sizes. The only issue is when we are going to place the prefabricated concrete slabs on the steel girders, then there has to be a provision for the shear studs. We should have a certain provision for shear studs. So we have to have certain holes already for the shear studs in these precast slabs, or the precast slabs can be of such size that they just fit into at that location only. And then the remaining portion of the holes, once these shear studs take their place in those holes, they have to be filled by non-shrink grout. So that's also, people are going also for composite beam with hollow core slabs. And now there are different types of shear connectors. We'll come down to that again as I've discussed in the next another presentation. The most popular is headed shear stud. Then you are seeing certain type of C-type shear studs, another type of shear studs. In all the shear studs, you will see that somehow effort has been made to ensure that there should not be a slippage between the steel girder and the concrete slab. That is, under the shear, the steel girder and concrete slab, they should not move away. Some of the classical examples of composite construction is Millennium Tower, Austria, a very big tower. So it's a 55-story building. And what is important is that the time of erection was just 8 months. So if you use a composite construction, then you can erect up to 55-story in just 8 months. This is the importance of showing this slide. So it was about, maximum speed was about 2 to 2.5 story per week, which is almost impossible when we go with the conventional concrete construction. So that's why this composite construction is becoming popular. Then another is of Citibank, and then a parking deck. So different type of composite constructions are being used. Here, what is interesting is that there's erection of composite columns over 2 stories. These columns are composite columns in the sense that outside there's a steel section, but inside they're filled with the concrete. And these composite columns, they're erected over 2 stories directly. And then there's assembly of prefabricated concrete slabs, of course. This is a typical cross-section of parking deck. And you can see there are a slim floor beam and slab, 200 mm concrete slab, 60 mm prefabricated concrete elements, and there's the in situ construction or in situ casting of 200 mm concrete slab. That's also an interesting method of going for the composite construction. You can have a small thickness of prefabricated slab. The advantage which you get with these prefabricated slabs is you get a place or you get a platform for working on it. So you don't need shoring and you don't need scaffolding, etc. The same prefabricated slab can be used for that purpose. And of course, here the headed stud size was 22 mm. The standard size worldwide is mostly 18 mm to 22 mm. So these are some other examples. Like you can see here again another type of composite construction. Of course, here inside there's a concrete core, and then there are composite beams, and outside also there are concrete columns. And you can see here, like this is a concrete core inside, which is connected through these steel girders, which will be made composite, of course, with time, with the outer core. So there's a connection of this steel frame to inner core. Again, this is another type of composite construction. You can have concrete filled steel column. You can see here that these steel columns outside peripheries of steel, but inside it is being filled by concrete. It is just opposite to our conventional concrete type of columns. You can have squared section columns also. So here you can see there's an inlet for concrete fill. So again, this is a composite column construction. And you can see here there are a lot of like shear struts which are protruding out, because when we'll cast the concrete around this, then that will ensure, these shear struts will ensure a good composite action between this steel section and concrete section. Of course, here it's for column, but the purpose of shear connection is same. So you can see here inside we have a steel section, then we'll have a concreting. And so a steel section embedded in a concrete column, again another type of composite section with a lot of shear struts. So you can see a lot of shear struts here. And here these different composite columns, there are a lot of composite columns, they will form a mega column here. Again, you can see here we are embedding like this steel, these composite columns in core wall. So different type of composite constructions have been shown here. Now coming down to that very important part, that is shear connections. So I'll just start another presentation. I hope the screen is visible, Vimal. Yeah, Vimal?
Yes, sir, it is visible. Yes, yeah. Yes, sir.
Now let's come down to the important part here, the research part. There are a lot of gaps we have already seen. Here we'll try to see an attempt to decipher the complexities of the shear connections, the way we moved ahead to find out something unique about these shear connections and to find out the new avenues where we can work upon. So first we'll see the importance of these shear connections and then we'll move forward. And before going for the shear connections, of course, we should have a robust knowledge of analyzing composite sections where the shear connections, of course, are 100% rigid. So this is a typical composite construction. If you see, that out of 100, maybe 95 type of composite constructions are of this type, where there's typically a steel beam, there's a concrete slab, and they're connected by the studs. So this is a quite typical composite construction. And if we talk about the service load behavior, all of us know is behavior for those loads which are acting in day-to-day life. We are not talking about the ultimate load behavior. Before that, going to the genesis of this type of section is that we do expect that the bottom portion will be in sagging or the bottom portion will be in tension. That's why the bottom portion or the lower portion will be in tension. That's why in lower portion we are putting steel, because concrete is weak in tension. And the upper portion we assume that will be mostly in compression. That's why in the upper portion we are putting concrete, which is okay in compression, but which is quite weak in tension. So this is a typical understanding of going for composite construction, that the steel girder should be placed down, concrete slab should be placed up, because the lower portion will be in tension, upper portion will be in compression. So the tensile part will be taken care by the steel beam, and the compressive portion will be taken by concrete slab. To talk about service load behavior of such structures, it's not always the idealistic case. If we go for continuous beams, then there will be certain hogging moments at the ends. Now, in the portion of hogging moment, the reverse will happen. The upper portion will come in tension and the lower portion will come in compression. That means that the concrete will now be subjected to tensile forces in the hogging moment region. And if those tensile forces cause a tensile stress, which is more than the tensile strength of the concrete, then the concrete is going to fail, or the cross section is going to be there, a simple steel cross section, because the concrete will fail. So if you see longitudinally the sections, then major portion, the section will be composite cross section. But in the hogging regions, the section may reduce to just a steel section because of higher tensile stresses. Then there are certain time-dependent effects of creep and shrinkage which cause progressive cracking here. So along with cracking, these creep and shrinkage add to the complexity of the behavior of composite structure. On top of that, there's a flexibility and type of shear connections, because we cannot assume that the shear connections are so rigid that they'll always ensure a composite action, 100% composite action. Because ultimately these shear connections are also made of steel. Even if it is a high grade steel, there's always going to be certain deformation on the steel section. So we cannot guarantee absolutely 100% composite action. Then there's a shear lag effect. Those who have gone through those composite beams, etc. The shear lag effect is that the shear stress is not uniformly distributed along the flange. And there are so many factors which are not there in the conventional steel construction or conventional concrete construction. So this leads us forcefully to nonlinear analysis. Of course, for nonlinear analysis, we require large computational effort. And the prediction of behavior of composite beams and frames, if we sum up this slide, becomes quite difficult because we have to consider cracking, creep, shrinkage, types of shear connections, etc. For that, some time back, we tried to propose a hybrid procedure, which is analytical at numerical level, to avoid the complexities of the finite element analysis. And also, we know that the finite element analysis cannot be performed in day-to-day life by the field engineers. So just to give a simplified solution, we assumed to begin with the shear connectors to be completely rigid, and we tried to develop certain solutions which can take into account cracking, creep, shrinkage, and all other aspects without considering the flexibility of shear connector. And we try to develop certain elements which are analytical at numerical level and analytical at elemental level and numerical at structural level. So these are like what we try to do is we try to split the total curvature, like total curvature was split in instantaneous curvature, And then instantaneous curvature was further split in instantaneous curvature due to moment, instantaneous curvature due to axial force. Similarly, strain was split in instantaneous strain plus time-dependent strain. Then instantaneous strain was further split in instantaneous strain due to moment, instantaneous strain due to force, etc. So different small components were made for these time-dependent these curvatures, the strains and the stresses. And at the elemental level, or rather at the cross-sectional level, we try to develop certain equations which can directly take into account the effect of creep and shrinkage. Here, like phi is denoting the effect of creep, phi is the creep coefficient, epsilon sh is denoting the shrinkage strain. So formulation was developed and the analysis was done in two parts. In first part, instantaneous analysis was carried out. In second part, time-dependent analysis carried out. Again, another interesting aspect if you're going to solve these composite structures is that it becomes an iterative procedure even at instantaneous part. The reason is initially you assume that there is no cracking, but once you get certain moments, you will come to know some part of concrete is going to crack. Then you have to carry out your analysis assuming those crack lengths. But once you'll go with those crack lengths, again you will get another set of crack lengths after the complete analysis. So there's a lot of iteration involved in the instantaneous analysis. And in time-dependent analysis, actually it so happens that these creep and shrinkage phenomena, they keep on changing the strengths and the stresses in the sections. That is, the crack lengths keep on changing as those portions where the tensile strength is lacking, the tensile stress keep on changing and the crack lengths will keep on changing. So here, cracked span length beam element along with closed form expressions were proposed. This is a typical span length beam element of a composite girder where the middle portion will be uncracked and the outer portions will be cracked. So you have to find out, like say, if you talk about the stiffness of a normal flexural member, then we say 6EI upon L square, 12EI upon L cube, 4EI upon L, so on and so forth. But they are applicable only when EI is constant throughout the cross section. But here, unfortunately, EI is changing with the cross section along the longitudinal section. So different integrations have to be performed to find out the flexural stiffness of such cracked sections. So again, certain integrations were performed, and based on those crack lengths, we tried to develop certain flexibility coefficients and rotation, fixed end moments, and mid-span deflections. Similarly, for time, you are seeing here with the time, the crack length will change. So different time intervals were considered. Typically 20 time intervals were considered. And we said that, of course, for a time interval, the crack length can be assumed to constant. Of course, the crack length will change each and every moment of time, or rather can change at each and every moment of time. But to begin with, it was assumed. Interestingly, if the crack lengths are changing, then the momentary distribution will take place, and again, new moments will be developed. So a complex set of history of moments has to be taken. So that was also considered into account. And if you see a typical composite frame element, it will be a 6-degree frame element as compared to composite beam element, which is a 2-degree frame element. So here, because if you're talking about frames, you have to consider axial and lateral degrees. So the process was extended there also. And of course, it becomes more complicated here because along with additional moments, additional axial forces are also developed. The procedure was validated with finite element software Abaqus. And we know that normally it happens that the computational effort required to solve any structure is roughly proportional to the square of degrees of freedom. So if we solve such type of composite frame by finite element software Abaqus, typically we'll need about 1500 degrees of freedom, whereas from the proposed procedure we'll need only 12 degrees of freedom. So about this 100 times difference in the degrees of freedom. And if we convert that to the computational effort, that goes up to 10,000 times. So you can reduce your computational effort at least by 1,000 times by going with this procedure, and you will get more or less the same results. And these are the like sort of validation results where we could achieve the experimental results. Then this modification can be done later on for concrete girders also, concrete beams also, if you wish. Here you can consider the cracking in the middle portion also, and you can develop the flexibility coefficient, etc. Coming down, then once we develop the complete knowledge of this, the composite structures with the shear, like or rigidly connected shear studs, we try to enter into new domain. That is, we try to see the effect of the flexibility of shear connection. And not only that, we also try to introduce a new type of shear connection. That's a epoxy bonded connection. Let's see what we have done. If we talk about the mechanical connection, then a typical mechanical connector looks like this. The advantages are there's efficient utilization and there's a transfer of forces. Limitations are there is a cause of stress concentration because they will be at certain locations only, and the entire shear force will be at those locations, concentrated at those locations. So there will be a stress concentration which can cause cracking of concrete. And of course, there will be a lot of shear stress distribution in those regions. If we can somehow replace this mechanical connector by the adhesive bond, then we can come out of this limitation of stress concentration. So if we put a layer of structural adhesive here, it is more or less like putting a layer of gum or glue or Fevicol between two that surfaces. So then there will be ease of construction. There will be uniform stress transfer because you can put this adhesive layer all along the longitudinal section, and there will be quality assurance. Of course, there are certain limitations that they can be susceptible to the environment because epoxies are normally susceptible to environment. And you have to also ensure the surface condition has to be very good. The reason is because when you will be using these epoxy adhesives, the thickness will be hardly 5 mm or 10 mm, not even more than 5 mm. And if there are undulations in your surfaces which are up to the range of 3 to 4 mm or 5 mm, then there is no purpose in using these adhesives because that there will be not proper bond. So that has to be ensured. This is the limitation. And of course, to check the strength of the shear connections, whether it is epoxy bonded or it is headed shear stud, there is standard test that is called push-out test arrangement, which is specified in Eurocode as well as in Indian standard codes. So what is done here is these concrete slabs are connected to the steel girder on both sides, and there are shear studs on both the sides or shear connections on both the sides. Then this steel section, a force is applied on this steel section. So this steel section tries to move down, whereas these concrete slabs, they are firmly placed on the surface. They will restrain this steel section from moving down. That will introduce the shear stresses between the steel section and the concrete slab. And then the load at which the shear connection is not able to resist that shear stress or shear force, which is arising due to the movement of the steel girder through the concrete slabs, that will tell us the total load carrying capacity of the shear connections. Of course, here say you are using two shear connections and you have got P, the failure is at P load, then each shear connection will have a strength of P by 2 load. And if it's a epoxy adhesive bonding, then that P divided by the area of that bonded area of that bonded part, that will give us the epoxy strength. Now to check the epoxy, what is very important is there's no standard epoxy as such available in the market for the composite action of structural steel and concrete slab. So a lot of epoxy, they were tried, different epoxies from different manufacturers, and even from the same manufacturer, different sort of varieties of epoxy. Like you can see, then the shear strength was checked for different type of epoxies. Finally, we could freeze on one epoxy, Sikador 30, which had a strength of 9 MPa. So we worked upon on that epoxy later on. Of course, here the mixing process is also shown. You have to mix epoxy for 10 to 12 minutes at 250 RPM. To go for an actual strength evaluation or to actually see what's happening, we installed a complete load frame, a full scale load frame. So it was a movable load frame sort of arrangement where we used, because a heavy load was about to come, we tried to cast a complete bridge. So we used underlaid piles also. Then we made a load frame structure base for load frame, and then a movable load frame was placed over there, and arrangement for loading was put there to see that what is happening actually on the full scale. And this is a typical diagram of the bridge which we cast at full scale. And we analyzed that through finite element also for both the support conditions. And we checked that through the experiments also, particularly for the epoxy bonding, one time for short term and another time for long term. Of course, one of the experiments that failed because we are not able to ensure a good surface, so the bonding failed there. But second time it was quite good. So this is the typical cross section and longitudinal section of the bridge which we use for full scale experiment. And here we are seeing the reinforcement which is laid in position before casting of concrete slab, the concrete slab after casting. And you are seeing the concrete slab in lifted position so that it can be bonded. And there were ISMB 200 steel sections. They were wrapped, of course, in plastic sheets after sandblasting. Sandblasting was done on these steel sections to ensure a proper bond between the concrete slab and steel girder. If sandblasting would not have been done, maybe epoxy would not have the proper bonding with the between the concrete slab and the steel section. And here in the last figure, you are seeing the bonding of steel beam and concrete slab going on. Here the concrete slab is now being lifted down, and here epoxy has already been placed on the steel section. And once concrete will touch that, then there will be a perfect bonding between steel girder and concrete slab. Then LVDTs were installed to measure mid-span deflection. Here you are seeing dial gauges are also there. LVDTs were also there. And this is a bridge which is under load now. And you can see there's an ample load as there. You can see the profile is not simple. Now there's a deflected profile. It's not along the horizontal line. There's a deflected profile. So there's so much load that the steel girder or the composite section is now showing a particular deflection. And initially we observed the cracks in the concrete at the mid support. Of course, before we reached to the ultimate load, what happened was there was a failure of welding at mid support. So it could have gone much ahead if the failure of welding would not have been taken place. So that means the failure was not due to epoxy here, the failure was particularly due to welding. Of course, that's experimental error. Welding can always be done better. And here the bridge is shown after failure. And that was the load displacement curve which was obtained at mid-span. And here you can see large deflection which is observed here, close-up of large deflection. So you can see here, this is one span, this is another span, the load is being applied at the mid-span. And of course, the load is coming from here, and then the load is getting transferred or being transferred at the mid-spans of both these spans. And so for long-term analysis, again, for next series of casting was done. And here, this time, it was ensured to have proper welding. And the strain gauges were put, LVDTs were put for long-term measurement. And of course, finite elements models were also developed. First finite element model was developed for short-term analysis. And the experiments and the finite element results were compared first with some other experimental results so that we are sure for our finite element results. And then we can compare it with our experimental results. So results were available in literature for experiments performed by Bozizoy et al. So we modeled that beam and we tried to see what are our results and what were his results. Our finite element results were matching with his experimental results. And then we developed it for long term also. And of course, before that, shear strength of epoxy adhesive was ensured was put as 9 MPa. And then this lambda, K, beta, etc. These are the properties which you need to put in Abaqus for Drucker pressure model. And ultimate strength of concrete, what we got in the lab was put, yield strength of steel, what was supplied to us. Failure load on each span was seen. And of course, here you are seeing there's a big gap between the experimental finite element model and experimental results. That was because of improper bonding in the first case and because of the failure of welding. Then in the long-term model, again, epoxy was modeled as C3D8R. The Drucker pressure model was adopted. And to check the actual strength of the epoxy, a single lab shear specimen was used, and we tested that in laboratory for a small UTM. And here you can see the experimental and the ASI results. They're almost matching in this case. And so there were certain scripts also which were written. The reason is that in Abaqus, there's an inherent disadvantage that you cannot use cracking and viscoelasticity phenomena, that cracking and creep phenomena together. So to take these two phenomena together, you have to use some scripts. So those scripts were written. And here you are seeing long-term results, even up to 250 days, more or less they're in agreement. So finally, that gave us a confidence on the model for this epoxy bonded connection. And of course, a quarter of bridge was modeled and general static analysis, tie connection was ensured. So these are standard terminologies of finite element method. They were adopted. And so here you can see the results. We also tried to see the effect of adhesive thickness actually, that does it affect the behavior of composite action. So we got some interesting results that when we used 2 mm thick layer, we saw a pure, and we used push out test, we saw a pure adhesion failure from steel concrete, the epoxy steel surface. So there's a pure adhesion failure here. But when we used a 3 mm layer, when we increased the thickness of the epoxy, instead of a pure adhesion failure, we observed intra-layer slippage. So that tells us that the thickness of epoxy layer is also quite important while defining the behavior of composite action or the composite behavior of epoxy bonded sections. So it is changing from adhesion failure to intra-layer slippage when we are moving from 2 mm to 3 mm thick layer. And when we moved to 4 mm thick layer, these intra-layer slippages were again predominant. When we further increased the thickness of epoxy layer to 5 mm, there were intra-layer cracks which were observed. So the behavior is changing from pure adhesion failure to intra-layer slippage to predominant intra-layer slippage to intra-layer cracks. So that also tells that it's also important to define an optimum thickness of epoxy for bonding of steel and concrete. Along with that, we also tried to see for the headed stud case that whether the behavior of this or the strength of these headed studs, you can see a lot of headed studs welded here, whether the strength of these headed studs in push-out test depends on the reinforcement or rather the nominal reinforcement which is generally put in the concrete slab, whether it depends on that reinforcement or not, because that reinforcement may also give some confinement effect to these headed studs, and that may help the headed studs in resisting more shear force. So different type of reinforcement patterns were used in the concrete slabs. There's a single layered, double layered with 100 mm case, double layered with 80 mm case, 60 mm case, even triple layered reinforcement cases. And you can see here that the ultimate slip is changing. If you're moving from single layered case where the ultimate slip is up to 15 mm, in triple layered case, the ultimate slip is only 7.8 mm. So there's huge difference between the single layered and triple layered. And similarly, the average ultimate bearing load, what we could see in single layered was 136 kilonewton. That load carrying capacity increased from 136 kilonewton to 170 kilonewton. In fact, when we move to triple layer, but it's not always that more number of layers are giving you more ultimate bearing. In fact, if you talk about just ultimate bearing, we observed better ultimate bearing in double layered with closely spaced spacing of 60 mm. That was 173 kilonewton. So the idea is that this reinforcement in the concrete slab also governs the load carrying capacity of these shear studs, which is mostly neglected in the course and mostly neglected by the researchers. So again, this is a niche area to work upon for future research. And these are the dimensional details of push-out test which were seen. We also tried to see what is the effect of impact loading, or rather, what is the behavior of these different type of shear connections, that is headed shear connection and epoxy bonded shear connection, on the impact resistance or impact load carrying capacity of these composite sections. So we used a sort of guiding assembly and impactor, that's a heavy this steel ball, and then the B is showing a casted specimen. And this is the manner in which in the C figure is showing in which the testing arrangement is there and how the load is being put on the specimen. So if you see the connection failure in case of adhesive bonded specimen, what we observed was initially there was a crack initiation near the interface of epoxy concrete interface, typically for that particular case which you observed, say for 39 blows. So there was a crack initiation. That crack led to final failure and consequent separation near interface after 43 blows. So within 4 blows, there was a final failure. And the concrete layer separated from each other. That means the bonded concrete was still stuck with the ice section. So as such, the epoxy itself did not fail. The failure was within the concrete itself. And then concrete layer from the bonded area gets removed from the slab with time. Now, if you see the connection failure of a stud connected specimen on the other side, then you can see here, this is the initial mark, level of mark on ice section. And this initial mark has shifted below. So there was a shift of ice section within 27 blows. So it required less number of blows and it started failing. What started happening there at 39 number of blows, that started happening at 27 blows only. And then cracking in concrete surrounded by stud was at 60 blows. Of course, that gives an important indication, though the initial failure started here earlier, but the final failure which was there at 42 blows is at 60 blows. That means the ductility, if you talk about the ductility part of this type of connections, then headed studs perform better. And if you are just concerned with the initial failure also, of course, then epoxy bonded connection performs better. And here you can see even the slip near the root of the stud also. We also tried to look into single span steel concrete composite beams with the staggered connections. Mostly people keep these shear connectors in the same line as we have seen in earlier presentation. But here you can see it is in a staggered manner. So one connection is here, another is here, one here, here. So it's in a staggered manner. So we tried to see whether that has an effect on the strength of the composite section, strength of the composite section or not, or strength of the composite beam or not. And of course, we found certain differences in the behavior when the connections were made staggered instead of in a single line. We also tried to develop a finite element model for composite structures with headed shear studs to see its behavior, which of course is much more difficult than the finite element model of epoxy bonded connection, because their epoxy can be layered as a layer, can be modeled as a layer. But here, of course, because it has a complex geometry, the headed shear stud, so you have to go for 3D modeling. So a solid 3D type deformable concrete slab has also to be created, because if you are modeling the shear stud as 3D, then you have to model other parts also mostly as 3D. And so we use 3D model here to use or to model a composite section with shear studs or headed shear studs rather. And of course, those who know the finite element modeling, then the shear connectors, you cannot make directly such geometry. So they were sketched and extruded over the top flange of the surface. And of course, this is how these studs were formed. And circular geometry also leads to creation of many improportional elements. So two diametrical cuts were put, and then a small circular cut was put. So a lot of manipulations in the geometry were done. Then we could arrive to the final section, which we were needing. And these are like showing the extended circular cuts, square cuts. And finally, we were able to model these headed shear studs, which of course requires a lot of time. But the idea is that now we have a finitely model for epoxy bonded connections also, as well as for headed connections also. And then, of course, the constraints, etc., we can apply as we do in regular finitely modeling. And the finitely model was validated with certain experimental results available in the literature, because we performed the experiments, full scale experiments, only on epoxy bonded connections, not on headed connections. For headed connections, we use just push out test. So certain experimental results were available, and we could see that the results were more or less matching. And of course, using this model, we can do many studies for service load behavior, etc. And so these are certain areas where we have been working, and where still there are a lot of or ample scope of opportunity to work upon. And any questions, any doubts? Yeah, Vimal, I think you can ask now.
Yes, sir. Dear participants, if you want to interact with the sir, Sandeep Chaudhary sir, please ask your queries. Sir, I have few queries regarding the
Uh-huh.
this composite construction.
Mhm.
One is that why we cannot use surface to surface interaction instead of modeling that epoxy as a by ductile pressure model.
Yeah,
If
because within epoxy also there is a slippage in the layers of epoxy also. We can do surface to surface, but then what between the layers of epoxy, because that also is a 3-4 mm layer. So within that, so there's a slippage. So that is the reason.
because the thickness is very less for epoxy, so
Mhm.
it unnecessarily increase the elements because we have to again we have to keep that
Yes,
aspect
but
ratio of the element.
yes, but that has the effect actually. If you see experimentally, then
Yes,
that has effect. Means if you model like just give a surface to surface connection,
yes,
then
sir.
normally there's a difference between the experimental and finite results. So which gives the indication that yes, something is happening within the epoxy layer also.
Okay, sir. And again, one more thing is that in the continuous beams,
Uh,
there are tension in some portion upside, some portion downside.
mhm.
So in that case, how can we take care of the concrete because it is weak in tension?
Yes, that is the reason precisely what was shown here. No? That's the precise problem. This is the slide what you are telling about. No? You're telling about.
Yeah, yes, sir, yes, sir. That's right.
So actually, this will lead to this the cracking here. So in the middle portion has a higher second moment of area or higher flexural rigidity, whereas
Okay.
the portions have lower flexural rigidity. So
So we
it's
have to.
with three different sections, being with three different type of flexural rigidities. So and that leads it to iterative process. So the only thing is that courts normally they say that okay, either you can find out these values of XA, XB, the correct length subjectively, or you can assume like 10 to 15% of the portion to be correct, like in Johnson's book and Eurocode it is given. But that's approximate method. But yes, if you are going for accurate analysis, there's no way out. You have to go for an iterative method only, because initially you don't know what is going to crack. So initially you have to assume everything to be uncracked. Then you'll get a crack length. Then you'll model it in three parts. Then you'll get another crack length. So it will be sort of iterative process.
And I have one more question regarding the campering.
Mm-hmm.
One is the heat campering and another is the cold campering.
Mm-hmm.
So in cold campering, we have applied some force with the help of
Mm-hmm.
jet.
Mm-hmm.
and after that force it bends, the beam bends.
Mhm.
So the applied force will be in the inelastic zone.
Yes, that has to be an inelastic zone.
So will not it affect the strength of the
Yes,
member because there is some residual strength?
no, that's why actually it's sort of not that simple. If you see, you have to apply that on in a particular manner. Means it's not a load is being applied at one location only. You have to apply the load at from multiple locations, and you have to apply the load in such a manner that only that part is going in elastic range where you are wishing. So it's not just one set of load; it is multiple set of loads which you are applying.
Okay, sir.
Hmm. Yes. Any other?
Because the maximum cambering, okay, so gradually we are applying the load along
Yeah,
the length of the,
gradually we are applying the load, but just a minute.
because the maximum bending moment will also occur at the mid span,
No, no, no.
and
That
again
is
the material become weaker in the longitudinal
no,
direction.
that is the there's a bit of difference here. It's just if you see here, it's the load is not being applied at one location. There are different like positions where different in different manner load is being applied. So maybe some portions will be kept in such a manner that they're completely means unaffected by the load because it's sort of like fixity in certain portions. And at those particular locations only that type of deformation will be ensured. It's not just a load from a single location. So means applying in a specialized manner. Yes. Any other?
For me, it is okay, sir. Other participant, if you want to interact with the sir, please ask queries because this is a very good topic and having a great scope in India.
So, and if you have some doubt in future, I think you can drop a mail to me also. And I hope that it will inspire at least a couple of participants to start the research in this area.
Yes, definitely.
Area to work upon. There's ample opportunity for like research abroad also because lot
Yes.
is going on there also. Okay.
So if nobody is asking questions, then we can close this lecture now. So thank you very much, sir, for your
Thank
for
you very
this
much.
important and informative lecture. You have started the lecture with the very basic and stressed why this particular area has a great research scope in India and also in the developing countries like India. Sir, you have stressed on the importance of the design of shear connectors and also focused on the key points that are associated with the composite construction. And also you stressed on the way of the connecting, how to connect the composite members with the concrete and the connections also. The failure modes of the stud and epoxy concrete composite is also discussed in detail. So this overall this lecture is very good and very informative, and I hope that the participant will definitely carry out some research in near future in this area. So I again want to thank you for accepting our invitation in very short time to present this lecture in this ESTC, sir. Thank you very much, sir.
Thank you, Raman. Thank you.
Thank you, sir. Thank you very much.